Okay. Let's start from the beginning. What are the four fundamental forces? Gravity is one of them.
Normal.
Hold on.
Oh.
These are the four fundamental forces. Okay? What do you know about gravity? Is it ever repulsive? No. Okay? Gravity is the sculptor of the universe. Without gravity, we wouldn't be here having this discussion. If you increase the distance between two objects, what happens to your gravitational force? It becomes less, because you're dividing it by distance. That's one of them. What's another one? No, not even close. Not even close.
Normal.
No, that's even worse. Oh, weak nuclear force. Whoa.
I get it now.
That was electromagnetic.
Oh, electromagnetic.
That was good.
No, it wasn't. It was the very first one. Strong. I looked that on yours.
Okay? Now, this is going to be on the multiple choice section of the test. Which answer are you not going to pick? No. 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 Weak. Okay? None of the answers are going to, I'm going to list it, don't pick it. Okay? Don't pick it. I'm not saying it's not important, I'm just saying it's not something we have to worry about in this class. Because without the weak nuclear force, our sun wouldn't be shining, we wouldn't be receiving radiation, we would be a cold, dark rock. Okay? So the weak nuclear force is important, just don't worry about it. So, if on the multiple choice section of the test, which is this is going to be, and I list these A, B, C, D, do not pick the weak nuclear force. It's not going to be one of the answers. Okay, I'm going to list it just to see if you pay attention. So, I'm going to ask you this question straight up. Which of the four forces is the strongest force? Strong nuclear. Do not miss this question. It's the strong nuclear force. And it has to be the strongest because that's what holds the nucleus together. Because protons don't want to be near each other because they have the same charge. They don't want to be near each other. They want to go flying apart. So the strong nuclear force has to be stronger than the electrostatic force which is trying to push them apart. If we did not have the strong nuclear force, we would not be here having this discussion because you could not form any kind of nucleus beyond hydrogen. Like you couldn't even make helium. Okay? The world, we couldn't exist, literally, there would be no helium, there would be no carbon, there would be nothing. Because if you didn't have the strong nuclear force to hold protons together, we wouldn't be here. Okay? So it's kind of important. But strong nuclear, it's a one-trick pony. It's a good trick, don't get me wrong, but that only exists within the nucleus of the atom. Very, 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 very strong, but it acts over an extremely short distance. Okay. The electromagnetic, that is the most diverse of all of these. This is what keeps my hand from traveling through the table when I put my hand down. That's what creates the force that holds two magnets together, let's say. Just hypothetically. It's what creates friction. It's cold outside. Oh, my hands are cold, but I've lost my mittens. Oh, you're going to do this, okay? That's the electrostatic force. It's the electrons in one hand, not liking the electrons in the other hand. That's what generates heat. That's what allows you to write. That's what allows you to see. So if I ask you something and it's not obviously gravity, it's not obviously the strong nuclear force, what's it going to be? Electromagnetic. I'm laughing on the inside. Okay. Newton's three laws. What's the first law of motion? No, that's the third law. Let me give you a hint. It's one word. Not Hank. What has more resistance to a change in velocity? Hank or Gary the golf ball? Hank does. Why? He has more stuff. Okay? So the first law basically says Hank's going to sit here until I apply an outside force to it. Mother Nature's a lazy prima donna. Mother Nature's going to sit here until an outside force acts upon it. Same thing is true with the golf ball. But when I drop them, when I drop Gary, which one's going to accelerate faster? Gary, the golf ball, or Hank? Or is it just going to be the same? Same. One of the main things I want you to understand is that when you have Hank and you have Gary the golf ball, is there more gravitational force acting on Hank? Absolutely. Doesn't FG equal mg? Is g the same for both of them, 1g? Yes, it's 9.8 meters per second squared. So, which one has more mass, Hank or Gary? Hank. Hank has more mass. Hank has a greater gravitational force. Gary just has a little gravitational force because Gary doesn't have much mass. Okay? Doesn't. Now, here's the story. When I let go of them, do they both end up with the same acceleration? Yes. Yes. But here's what I want you to see, is that the reason they end up with the same acceleration is because that force is proportional to mass. Gary has less mass, there's less force, but he has less inertia. It's easy to make Gary accelerate. Hank, a lot of stuff. Tough to get Hank to accelerate. But once Hank gets moving, guess what? It's hard to stop Hank, which is why I'll put my hand underneath and let Gary fall on him. I'm not going to do that with Hank, okay, because my hand would most likely break. Cool with that? Got it. Okay. I promise you there's going to be a rocket problem. Mark my words. Promise you. Okay, it's going to be in the bottom front page. At a minimum, that's where the first one's going to be. I'm going to give you the mass of the rocket, maybe 5.60 kilograms. And I'm going to tell you the upward force from the engines is 120 newtons. And I'm going to ask you to calculate the acceleration of the rocket. Could I just take 120 newtons and divide that by 5.6 kilograms to get my acceleration? Matty Hill, you shake your head no. Why not? F equals ma. There's my force, there's my mass. Easy peasy. Yes. You have to pay off the Gravity Mafia. How much money does the Gravity Mafia charge per kilogram? $9.80. Okay? That's the payment per kilogram. $9.80. So, somebody take 5.6 times 9.8.
54.9.
54.9. So out of the 120, I've got to give $54.90 to the Gravity Mafia. Okay? What's left over is what I can use to accelerate the rocket. So, it's going to be in the bottom front page. It's going to be a problem like this. I'm going to ask you to make a free body diagram. You're going to have your applied force going up. You're going to have your gravitational force going down, which in this case is negative 54.9 newtons. Boom. There's your net force. And as long as that net force points up, you're going to have an acceleration. What's the only time you don't have to pay the Gravity Mafia? If you're in deep space. Unless I explicitly tell you differently. You always pay the Gravity Mafia. If I do not want you to worry about gravity, I will tell you. I will tell you. The effects of gravity can be reasonably ignored. Unless I tell you that, you pay off the Gravity Mafia. We take the same rocket. We go to Mars, where G on Mars is about 3.6 meters per second squared. What's going to happen to your opposing force? Bigger or smaller, stay the same? Smaller. Okay? Because of the fact that now you don't have to pay the Gravity Mafia as much. So if I have the same applied force of 120 newtons, and I'm on the Mars, what's going to happen to my net force? Same 120, I don't have to pay as much money to the gravity mafia. Net force is going to go up. What's going to happen to the mass on Mars? Do not make this difficult.
Stay the same.
Say the exact same. Mars is a measure, or mass is a measure of stuff. If I'm on the Earth, Moon, Mars, Jupiter, Saturn, deep space, the amount of mass isn't going to change. Okay. I promise you, there's going to be a problem where you're going to have like an Atwood machine, where you're going to have like 220 grams on one side and 200 grams on the other. Okay? Which one do you call the applied force, the bigger or the smaller? Morgan. So that's going to be 0.22 kilograms times G. That's going to be your applied force. This is going to be your opposing force, which is going to be 0.2 kilograms times G. How are you going to get the net force? Jackson.
You add your applied and your opposing.
But one's going to be positive, one's going to be,
Negative.
you're going to get your net force, then you're going to divide by the mass. Do I divide by the 220, the 200, or the combined mass?
Combined.
Always divide by the combined mass. That's going to be one type of problem I promise you is going to be there. I promise you there's going to be a problem where you're going to have a block and it's going to get drug along like this. Okay, I promise you there's going to be one like this. It's on that lab that I just gave back. You had like a 220 gram mass on the end and you were dragging the 200. This is going to be the last problem on the test. I'll tell you where it's going to be. It's going to be the last problem on the test. Situation number one, there will be no friction. What's the only force available to make it move? Gravity pulling down on that. You get that divided by the total mass. If there's friction, and there's going to be that on the second part of the problem, it's only that mass that determines your frictional force, because that's where that interface takes place. So, on the review, you got the blank version, you got the answer keys. So, like for example, here on number 17, you've got two situations. One where it's just a friction of the surface, one where you have friction. Make sure that you can do 17. Here's one on inclined planes. I promise you there's going to be an inclined plane problem. Here's one where you have that Atwood machine, where you have two different pulleys. So if nothing else, make sure that you can do 17, 18, and 20. Okay, literally, if you're pushed for time, make sure that you can do 17, 18, and 20. On the front, number 6, this is the liftoff of the Saturn V rocket. Here's your rocket problem. So if you do nothing else, make sure that you can do number 6, 17, 18, and 20. If nothing else, you make sure that you can do those. All right, I'm done. Stop you under camera. If you